All right, we're looking at Chapter P, Notes B for AP Calculus. You'll see we're starting with graphing by plotting points, and it says all points on the graphing equation make that equation true when substituted into it. And we want to graph 3 minus x squared. Now, you might have an idea of what this graph looks like without plotting points, but just to confirm our thoughts, we're going to plot at least 2 or 3 points on the graph and see what we have. So we're just going to make a little table over here. I'm going to plug in -2 into 3 minus x squared. So that's going to be 3 minus -2 squared. And you're going to want to be careful here. The temptation for some of you might be to see these two negatives right next to each other and say, oh, those are going to cancel and become positive. But that's not true, because if you think about order of operations, before you add and subtract or before you multiply the two negatives, you have to do exponents. Please excuse my dear Aunt Sally. PEMDAS, exponents comes first. So I need to calculate -2 squared before I look at these two negatives. So that's going to be 3 minus 4, which equals -1. So the order pair we have there is -2, -1. And then we'll go ahead and plug in 0. That's going to be 3 minus 0 squared, which is just 3. So the order pair is 0, 3. And we plug in 2. So we're going to have 3 minus 2 squared, which again gives me 3 minus 4, which is -1. So 2, -1. 0, 3, 2, comma 1, 2, -2, comma -1. Sorry, comma -1 there. And as I mentioned, you should have an idea of what this looks like. X squared, you should know that that's going to be a parabola. And with the negative, it's going to be opening down. And you kind of see that. We've got a parabola looking like it might be opening down right here. And it's good. It's shifted up 3 units. So yeah, that's just symmetric about the y-axis. And you have a graph that looks like that. Now I'm just going to draw a graph here. Let's just draw a nice curve through these points. And basically the x-intercepts are where the graph crosses the x-axis. So our x-intercepts are here, here, and here. So for this particular graph, we have x-intercepts at x equals -4, x equals -2, and x equals 6. And this is just a picture that I made up, right? I just drew a curve so that we'd have some x-intercepts. Okay. Now, at the x-axis, the y-coordinate is 0. So if I'm given a function and I want to find the x-intercepts, you just set y equal to 0 and solve. And so that's exactly what I'm going to do right here. I have y squared. We just put 0 in for y. 0 squared equals x to the 4th minus 4x squared. And 0 squared is just 0 equals, that's a 0, x to the 4th minus 4x squared. And in order to solve this, we're going to have to solve by factoring. And it looks like I can factor, and greatest common factor is x squared out of both of those. So that's going to be 0 equals x squared. And if we factor out x squared, we still have an x squared there, minus factor out x squared, so we still have a 4. Remember, factoring and distributing are inverse operations, meaning they undo each other. So factoring is like dividing, because distributing is like multiplying. You better be able to multiply x squared and x squared and get x to the 4th. you better be able to multiply x squared and negative 4 to get negative 4x squared. Otherwise, something went wrong. So anyway, from here, I see the zero product property, meaning when we multiply two values together and get 0, at least one of these values must equal to 0. So that means x squared equals 0, or x squared minus 4 equals 0. And we're just going to solve those. To get x by itself, you square root both sides, and that's going to give me x equals 0. Here, you could factor using the difference of two squares if you really wanted to, but I'm just going to solve with square roots. I'm going to add 4 to the other side. Get x squared equals to 4. And then square root both sides. And you're going to want to be careful. Some people will make mistakes right here. They're going to write, okay, x equals 2. And they're going to be happy, and they're going to go on their way feeling pretty good, but they forgot something right here. Remember, when you square root both sides of an equation, you end up with plus or minus 2. The reason we didn't put plus or minus here is because it was 0, and 0, positive or negative, it doesn't change anything. It's still just 0. It's neither positive nor negative, so we didn't put plus or minus there, but if it was anything other than 0, we would have a plus or minus. All right, looking at the next page. The y-intercepts of a graph are where the graph intersects the y-axis, and so I'm just making up a graph here. And what you can see is the y-intercept is right there where it crosses the y-axis. That's at 0, 2. And so the y-intercept equals 2. Now, just like when we were finding the x-intercepts, we set y equal to 0 and then we solved. If we want to find the y-intercepts, we're going to set x equal to 0 and then we're going to solve for y. So it's the same idea, we're just substituting 0 for x instead, whereas when we were trying to find the x-intercepts, we substituted 0 for y. So anyway, let x equal 0. So y squared equals 0 cubed minus 0 plus 4. And the zeros are going to go away. We're going to end up with y squared equals to 4. Square root both sides. And so we end up with y equals, I just said it on the previous page, we're square rooting two sides of an equation. Don't forget plus or minus 2. And so the y-intercepts are 0, 2 and 0, negative 2. And if you just put plus or minus 2, that's fine. I just wrote the ordered pairs there. I was getting a little bit overexcited, so I went with the ordered pairs. But if you just put y equals plus or minus 2 for the y-intercepts, you're in good shape. Now, how could there be two y-intercepts? How could there be two y-intercepts? Most of the time when we see a function, we only have one y-intercept. This is a cubic right up here. Well, the answer is this is not a function. This is not a function. An example that you might be familiar with, and this is just a new example I'm going to draw over here just to give you a visual representation. If I had something like y squared equals x plus 2, this is something you might know what this looks like. If you square root both sides, you end up with y equals plus or minus the square root of x plus 2. And so when you go to graph, if you remember what square root of x looks like on the graph, from trig or algebra 2, it's a square root function, and plus 2 underneath the radical means it's going to move to the left 2 units. So this graph moves to the left 2 units and looks something like that. Well, that is square root of x plus 2. That's square root of x plus 2. But this is y equals square root of x plus 2, and y equals negative square root of x plus 2. Well, the negative reflects the x-axis. The negative on front here is a reflection of the x-axis. And so that piece is right here. That's negative square root of x plus 2. So there you see, we have this function. This is the graph. This is the graph of this, okay? And you'll notice it does have two y-intercepts here, right there and right there. All right, so that's kind of how that became possible. Hope that helps. All right, now, symmetry with respect to the y-axis means it's a mirror image of itself about the y-axis. Basic thing that is symmetric with respect to the y-axis is a parabola. If I look at this, I'm just going to draw as best I can. I just drew a parabola here, and you'll notice on the y-axis, if you drew a line right here and split that graph in half, those pieces would fold onto each other, right? If I could crease this exactly down the red line right here, exactly down the red line, you see they would fold right on top of each other if I just folded that paper. And so that's symmetric about the y-axis. It doesn't have to be a parabola. I mean, it could be a lot of different shapes, just a different one here. If I had something like this, that's symmetric about the y-axis also. Well, my drawing didn't come out that great, but if you can imagine this drawing is perfect, you could draw a line there, and you could fold those on top of each other if you creased it down the red line. Okay. Now, in order to test for symmetry about the y-axis, we're replacing x with negative x in the equation. Look at this. If this ordered pair is x comma y, this ordered pair is on the left-hand side of the origin, so x is negative. That's negative x comma y. And that would be true for any pair. If there's an ordered pair here, there's a ordered pair over there, that's negative x comma y. So if it's symmetric about the y-axis. So in order to test, we're going to replace x with negative x, and if the equation is equivalent, then it is symmetrical about the y-axis. If it's not equivalent, then it's not symmetrical about the y-axis. So let's just do that. Y equals negative x squared minus 3 times negative x. And then negative x squared, that's going to become positive. Y equals x squared. Negative times a negative is positive, plus 3x. And I have to ask myself, is this the same as that? And the answer is obviously no. This is plus 3x, and this one's minus 3x. So the answer is no. Okay, it is not symmetric about the y-axis. Now, over here, same test. Plug negative x in. Y equals negative x to the fourth minus 2 times negative x squared plus 3. And then we'll simplify as much as we can. We have y equals the 4, the power of 4 means there's 4 negatives, meaning they'll all pair up and cancel out. So that's going to become positive x to the fourth. Same thing here. I mentioned this earlier. do exponents before multiplication, order of operations. You need to do x squared first, negative x squared first, not negative 2 times negative x. Okay, do not do negative 2 times negative x. You have to do the exponent before multiplication. Negative x times negative x is positive x squared, so minus 2x squared plus 3. And this is exactly the same as the original equation. X to the fourth minus 2x squared plus 3. So yes, this is symmetric about the y-axis. All right, moving on. Now we're looking at symmetry with respect to the x-axis. And I actually drew a graph of something that was symmetric with respect to the x-axis earlier. And you'll see it looks familiar. Again, my hand drawing may not be perfect, but that's okay. Now you can see if I could fold the paper on the red line, you know, these two pieces of the graph would just fold right on top of each other if I just creased it on the red line. And so that's symmetry about the x-axis. Same principle here. Over here I have some x comma y. Well, what's the ordered pair down here directly across the x-axis? If this is x comma y, this ordered pair, we moved down. We still went to the right the same distance. Left and right is x, up and down is y. So we went down, this is x comma negative y. And so in order to test for symmetry about the x-axis, we replace y with negative y into the equation. And same thing, if the equation is equivalent, then it's symmetric about the x-axis. So let's do that. We're replacing y with negative y equals 2x squared plus 1. And then I'm going to get y by itself, divide by negative 1. So we end up with y equals negative 2x squared minus 1. And you have to ask yourself, is this equivalent to this? And obviously it's not. This is positive 2x squared. This is negative 2x squared. They're not equivalent, so this is not symmetric about the x-axis. Same test over here. Negative y substituted in for y. So we have negative y squared equals 2x cubed plus 4. And then simplify, negative y times negative y is y squared equals 2x cubed plus 4. And if I look at that, this looks exactly identical to the original expression, the original equation. So yes, this one is symmetric about the x-axis. Now, last piece is symmetry about the origin. All right, the most obvious function that's symmetric about the origin is the cubic function. And so it looks something like, let's see here. It looks something like that. And you'll see we have this ordered pair x comma y. Well, over here, there's this corresponding point on the other side, and we went from here and we went over the y-axis, we reflected over the y-axis, and we reflected over the x-axis. And so that ordered pair is negative x comma negative y. And what that means is that when we test for symmetry about the origin, we're replacing x with negative x and replacing y with negative y in the equation. And when we simplify, if the equation is equivalent, it is symmetric about the origin. If it's not equivalent, it's not symmetric. So we're just going to do that test. We're replacing both x and y with negative x and negative y, and we're going to see if we get an equivalent equation. So y squared is going to be negative y squared equals 5 times negative 1, negative x cubed plus negative x squared. So we replace y and x with negative y and negative x. And then we start to simplify, even power, so the negative goes away, that's y squared equals, this is an odd power, a power of 3, so there's going to be a negative left over, that's going to be negative 5x cubed. Even power, the negative goes away, plus x squared. And then I have to ask myself, is this equivalent to this? And the answer is no, because we have positive 5x squared here, but this one's negative 5x squared. So no, this one is not symmetric about the origin. Now, look at this piece right here. We've got negative y equals 3 times negative x cubed minus negative x. So I made the substitutions. Now I have to simplify and see if I can get this same equation. Negative y equals, remember odd exponent, this is going to stay negative. So that's going to be negative 3x cubed. Two negatives here are going to cancel out and become positive x. And it doesn't look the same yet, but there is something we can do that can adjust this equation a little bit. Notice I have negative y right here. What would happen if I got y by itself? I'd be dividing everything by negative 1. And when I do that, we end up with y equals 3x cubed minus x. And looking at that, it looks like 3x cubed minus x, 3x cubed minus x, those are equivalent. So yes, this one is symmetric about the origin. All right, now we're going to use these skills. We're going to make a little graph based on what we know. We're going to combine everything, find the intercepts, x and y intercepts, determine the symmetry, use it to help you sketch the graph. So, x-intercepts. We set y, get that on the camera here. X-intercepts, we set y equals 0. So 0 equals third root of x squared minus 1. So to undo the third root, we take the power of 3, and whatever you do to one side, you have to do to the other side. So 0 cubed is 0 equals, and those cancel, x squared minus 1. And then we solve for x, plus 1, 1 equals x squared. Square root both sides. Remember, when we square rooting both sides of the equation, you should get x equals plus or minus 1. Okay. So what that means is if I look on my graph, I know that there are x-intercepts at negative 1 and positive 1. Now, we're going to test y-intercept here as well. And to find the y-intercept, we set x equals 0. So that's going to be y equals the third root of 0 squared minus 1. So that's equal to the third root of negative 1. And you can take the third root of negative 1 because the root is odd. So negatives are okay because negative 1 times negative 1 times negative 1 does equal negative 1. So that's equal to negative 1. So I know that over here on the y-axis, My graph's going to cross right there. Now, that doesn't mean that this is a parabola just because we've got a couple of points that look like it could be. We need to figure out what the symmetry is. We may have to even plot a couple of points and get a little bit better idea of what the graph will be. So I still need to figure out the symmetry. So let's test symmetry with respect to the x-axis. And if you remember to test that, we substituted negative y in for y. So negative y equals the third root of x squared minus 1. And so if we divide by negative 1, divide by negative 1, y equals negative the third root of x squared minus 1. And so these are not the same equations, so no, it is not symmetric about the x-axis. So we're going to keep going. We're going to test if there's symmetry about the y-axis. And to test for that, then we substituted negative x in for x. So that's going to be y equals the third root of negative x squared minus 1. And this goes all the way there. And negative times negative is positive, so that's going to be third root of x squared minus 1. And that is the same equation. So that means it is symmetric about the y-axis. And I'm also going to test symmetry about the origin. Okay. So we substituted for y and x. We're going to have negative y equals the third root of negative x squared minus 1. So negative y equals the third root of x squared minus 1. Divide both sides by negative 1. We get y equals negative the third root of x squared minus 1. And so no, it is not symmetric about the origin. It's symmetric about the y-axis. Now, maybe to get a little bit better idea of what this might look like, I'm going to plug in a couple of points. So I'm just going to go on the side here and make a table. I'm going to try plugging in 3. I chose 3 specifically because it was outside the points I already knew. And I was thinking right here, the third root of 8, I know. And if I plug in 3, that's going to give me 8. So that was helpful. Third root of 3 squared minus 1. That's the third root of 9 minus 1, which equals the third root of 8, which is 2. So we have the order pair 3, 2. If I plug in negative 3, it would be the third root of negative 3 squared minus 1. And I can kind of tell that's going to actually give me the same thing. It's going to give me 9 minus 1 again. It's going to give me the third root of 8, which is still equal to 2. So we have negative 3, 2. Now, be careful. This is not linear. This is not linear. This is a curve. So it's going to look something like that. So you can see it has some of the qualities of a parabola, the symmetry around the y-axis from the x squared, but it also has a little bit of shape on the end based on the third root. So you see a couple different things coming into play there to kind of determine the shape of this graph. If you didn't know based on plugging in these points, then plug in some more points. Plug in 5 and negative 5 and see what it looks like. And you're going to see it's not going to be a line. It's getting flatter out here if you plug in 5. So if you're not sure, plug in as many points as you need and go from there. So, all right, last piece. Find the points of intersection. Use substitution or elimination. This one is set up for substitution because I have y by itself already. So I can just take this and substitute into the other equation where y is. So we're going to end up with negative 4x equals 2 times 2x squared minus 4. And then we distribute the 2. So we end up with negative 4x equals 4x squared minus 8. And I'm trying to solve for x. Because I have x squared and x, I'm probably going to have to solve by factoring. So add 4x to the other side. We get 0 equals 4x squared plus 4x minus 8. And I could factor the way it's written, or I could use the quadratic formula. But if you recognize there's a GCF, a greatest common factor here, that's going to make this a little bit easier. I see I can factor out a 4 out of all of these. So we end up with 0 equals 4 times x squared plus x minus 2. And that makes that much easier to factor. I can just find what multiplies to negative 2 and adds to 1. Okay, and I got that from right here. What multiplies to negative 2. And the 1 is the coefficient of x, just in case you forgot some of your factoring skills. And so I need numbers that multiply to negative 2 and add to negative 1. That's going to be negative 1 times 2 and negative 1 plus 2. So we end up with 0 equals 4 times x minus 1 times x plus 2. And then we use a zero product property. We have to set x minus 1 equals 0 and x plus 2 equals 0. So x equals 1, x equals negative 2. So we're going to have intersections at 1 and negative 2. By the way, no reason to set this equal to 0 because there is no variable, right? It's just 4. Over here is where I can solve for x. So that's what I needed to set equal to 0. 4 is just 4. There's no variable to solve. So 1 and negative 2, I'm going to plug that back into one of the equations, whichever one I think looks easier. It doesn't matter what you choose. You can choose the top one or the bottom one. The top one, y is solved for already. The bottom one maybe is a little simpler. It really doesn't matter. So for x equals 1, I'm going to plug into negative 4x plus 2, not plus 2y, negative 4x equals 2y. And so we're just going to plug in 1. So that's going to be negative 4 times 1 equals 2y. Negative 4 equals 2y. Divide by 2. Negative 2 equals y. And so the ordered pair there, 1 comma negative 2. I'm going to do the same thing, substitute negative 2. So we end up with negative 4 times negative 2 equals 2y. Negative 8 equals 2y. We can divide by 2. So we end up with negative 4 equals y. And the ordered pair is negative 2 comma negative 4. I think that should be good. Oh, I made a little mistake here. Negative times a negative is positive 8, which makes that positive 4. So they intersect at negative 2, comma positive 4. Almost made it through the whole thing with no mistakes, but that's okay. It happens to the best of us. Hope this helps. By the way, the reason you can have 2 points of intersection here is because one of these graphs is not linear. So that's why you can have 2 points of intersection. We've got 2x squared minus 4, and then this one's a straight line. So one of them's a parabola. You got a graph that looks something like this. And so you see it intersects in 2 different places. Okay. So anyway, that's it for today. That's section B. Hopefully that helps.